So resonance is what we'll talk about now. Just give me 2 minutes here. Not even 2 minutes, less than that. Resonance. So resonance basically means there's more than one structure. I should say more than one equivalent structure. That's very annoying that the projector blurs and unblurs, but it's more than one equivalent structure. So there's more than one. It's not like one structure is better than the other. They're all kind of equal, and they actually, go from one to the other equally. All right, so an example of this that we'll start off today is carbonate ion. Okay, do you remember this from your flashcards all the way back? Okay, carbonate ion. So we're going to do the Lewis structure of carbonate ion. All right, so what is carbon happy at? Remember from last lecture? Excellent, very good. Happy to hear that. What is oxygen happy at?
6.
Very good. And how many oxygens do we have? 18. And what does the -2 tell you? Okay, so the -2 tells us that carbonate, CO3, gains 2 electrons. So we have to add 2 electrons to the structure. So how many total electrons do we need to fill in? Okay, so our job is to get 24 valence electrons around carbonate. Okay, so what do you guys think our central atom will be? Carbon, very good, thank you. What does carbon love? It doesn't just happy at 4, but it loves 4. So how will it get to 4 when there's 3 oxygens? 1 double bond to what? And then, okay, so that's 1. What about the second and third oxygen? This is going to be a single bond. Okay. Is that it? Is this what you'll put on the exam? Okay, if I ask you for the structure of carbonate, is this what you'll put? Okay, what else is left? We need to put all the electrons here. So we have 1, 2, 3, 4, 5, 6, 7, 8. Where do the other electrons go? Okay, lone pairs. So you guys tell me. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Does that look right to you? Okay. Without looking on the computer, okay, without looking on your phone, you should be able to do this. Okay. So why did I make this arrangement like this? First of all, is this the right structure? The answer is yes. Okay, it is the right structure. It is. All right. So these are our 24 electrons. There are 2 things we have to do. Okay, one is the octet rule. Okay, and the big one. What's the big one? I'll put it in red ink. Minimize what? Minimize formal charge. Very good. All right. So let's first do the octet here. Okay, let's do carbon. Okay, everyone count with me. 1, 2, 3, 4, 5, 6, 7, 8. All right, carbon is fulfilling the octet. Now let's do the happy formal charge. Actually, formal charge. Ready? Count with me. This is formal charge now. 1, 2, 3, 4. What is carbon happy at? 4. What's 4 minus 4?
0.
Correct. Okay, the formal charge on that carbon is 0. Let's do this topmost oxygen. Okay, ready? Let's do octet. Ready? Count everything, shared and unshared. So these are unshared, or lone pairs. 1, 2, 3, 4, 5, 6, 7, 8. This oxygen has an octet. Very good. Now, one of the more important things is formal charge. Okay, formal charge considerations. Ready? Here we go. 1, 2, 3, 4, 5, 6. What is oxygen happy at? 6. What's 6 minus 6? Is 0. Okay. All right. Let's look at this oxygen, which will be the same as that oxygen. All right. We'll do the octet rule first. All right. Ready? 1, 2, 3, 4, 5, 6, 7, 8. Okay. Octet rule satisfied? All right. Now let's do formal charge. Okay, ready? Count with me. 1, 2, 3, 4, 5, 6, 7. 7. What is oxygen happy at? 6. What's 6 minus 7? So this oxygen has a -1 charge. Okay, will it be the same for this oxygen?
Yes.
Okay, I'm not going to go through all that counting again, but the answer is yes. Okay, what's the total charge? -1, -1. What's the total? -2. What's the total charge in the original problem, original structure? -2. Okay, so this is the Lewis structure of carbonate. All right, but that's one answer. Okay, you put this answer on the exam. That's good. Everything has an octet, and then the formal charge is accounted for, -2, -2. But what other structure could exist?
The one at the top moved to the bottom.
Say it again?
The one oxygen at the top moved to the bottom.
Nah, that's just flipping it. Okay, what else could we do? See that double bond? What can we do with that double bond?
On the ends.
Yeah, I just put it on top, okay? I can also put it where?
On the side or so.
On the sides. Okay, so how many total structures are there?
3.
3. Okay, so that's the example of resonance. All right, so I'm going to put it on this side. All right, so I'm going to move this pair of electrons here. That kicks this pair of electrons out. Okay, I'm going to draw a back and forth arrow. Okay, so make sure you do this on the exam. Okay, and now the double bond, where is it at? It's on the side. Okay, where is this oxygen? What type of bond is with this oxygen on top? Single. Okay, what about this oxygen on the right-hand side? Okay, what do we know about a single bond oxygen with 3 lone pairs? What is its formal charge?
-1.
What do we know about an oxygen, 3 lone pairs with a single bond? What is its formal charge? -1. Okay, so that's one structure. And can anyone tell me the last structure? To the right, double bond to the right, good. So I'm going to move this pair of electrons here. That kicks out this pair of electrons there. It doesn't matter which electrons, it doesn't matter. Okay. Bless you. Okay. Bless you.
Can we not do the double bond down?
Double bond down?
Yes.
What do you mean
Instead
down?
of having it up, down.
It's the same thing. All you're doing is just flipping the molecule.
Fine. Yes.
It's the same thing. So you can, I mean, I drew it up, but you can draw it down. It doesn't matter. What's the formal charge of an oxygen with a single bond, 3 lone pairs? -1. And, by the way, what's the formal charge of a double bond oxygen with 2 lone pairs? 0. Everyone see that? If you have a double bond, 1, 2, 3, 4, 5, 6, what is oxygen happy at? 6. 6 minus 6, 0. Okay, so this is the structure of carbonate, which illustrates resonance. Why do you think carbonate is so stable, or any molecule that has resonance, it being so stable? Okay, because where's the negative formal charge? It's shared. Okay, it's shared. Okay, where's the double bond? Okay, in one structure it's here, in one structure it's here, in one structure is here. So it's shared. You see that double bond, you see that negative charge. It's not just localized to one atom. Okay, it is, you know, a bee buzzing. How does a bee buzz? Okay, it's like buzzing. It's like moving around. So this gives carbonate very exceptional stability because that negative charge is shared equally across the 3 oxygen atoms. Furthermore, that double bond is shared equally across all 3 oxygen atoms. It's not like this structure predominates over that. It's equal. So there's really 3 structures merged in one. And this is called delocalization. Have you heard this term, delocalization? So that double bond is not localized to one, entity. It's shared equally. Okay? So we have delocalization of the formal charges, and we have delocalization of the double bond. So this gives, carbonate a lot of stability. Okay? Carbonate is very stable. All right, shall we do one more resonance example? Or maybe 1 or 2 more, then we'll move on to something new. Another example of resonance is nitrate. Remember nitrate from our flashcards? Okay, what's the structure of nitrate? Nitrate. Okay, this is the nitrate ion. All right, what is nitrogen happy at? Very good. Nitrogen is happy at 5. Okay, what is oxygen happy at? Okay, times 3 is 18. And what does the minus sign tell you? Yes, we add an electron. So just like before, just like in our previous problem where we had 24 valence electrons that we need to fill up, okay, for nitrate we need the same, right? 24 valence electrons. All right, what do you think our central atom will be? It's going to be nitrogen with bonded to how many oxygens? 3. 1, 2, 3. Okay. So how will we get to minus? Remember, how do we get a minus in a formal charge with an oxygen? How do we get a minus formal charge with an oxygen? Because here, how many minuses do we have?
1.
So how will we get a -1? We can do what to an oxygen? Say it again. So we can make a single bond to an oxygen. What will that charge be? So there's our -1. So we'll make a single bond to the oxygen. So how many lone pairs on this oxygen? Okay, there's that. Then what about the other oxygens?
They have to be double bond.
They'll have to be double bonds. And what do we know, Gerardo, about double bond oxygen? How many lone pairs? Two. Very good. Okay. And do we have 24 valence electrons? Let's check it out. All right, count with me. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. There we go. Okay, we got 24 valence electrons. All right, let's do formal charge and octet rule. Okay, we'll first start out with the formal charge for nitrogen. Formal charge for nitrogen. Okay, ready? 1, 2, 3, 4, 5. What is nitrogen happy at? 5. What's 5 minus 5? Okay, let's do the octet rule now for this. Okay, what is the octet rule? Ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we can call this an expanded octet. Yeah, very good. Okay, it's okay. Remember, the octet rule is 8, but for some they can get an expanded octet. Why would this want to form an expanded octet? Because the formal charge is 0, which is a good thing. Okay, what's the formal charge on this oxygen? Shall I do this again? 1, 2, 3, 4, 5, 6, 7. What is oxygen happy at? 6. What's 6 minus 7? -1. Octet. You guys should know this by now, but I'm going to keep on doing this. I'm going to do it. Drill it, drill it. 1, 2, 3, 4, 5, 6, 7, 8. Octet rule satisfied. What about this double bond oxygen? Formal charge? 1, 2, 3, 4, 5, 6. What is oxygen happy at? What is 6 minus 6? 0. Octet rule? 1, 2, 3, 4, 5, 6, 7, 8. Octet rule satisfied. Okay. So this is the right structure of nitrate. Do you see any other structures that you can see or think about?
Yeah.
Okay. What would be one, Husong?
Maybe the single bond shift to the left or to the bottom.
Okay, very good. The single bond can either be at the bottom or to the left. This makes nitrate very stable. Okay, nitrate is a preservative. It's found in Spam. I know this. They put a lot of nitrates in Spam. You know Spam, the meat, if you call it meat. So it's like a very good preservative. It's very stable. Okay. Yeah. All right. So let's do what Husan told us to do. You see this single bond oxygen? I just put it here on this side, but that's really, arbitrary. So I can also just as well put it, that single bond to the bottom. Okay, so this pair of electrons moves here, it kicks out this pair of electrons and moves it down there. Okay, that's one way you can do it. And then, so the single bond is at the bottom. Okay, negative formal charge at the bottom oxygen. And then, what's the last one? Single bond where? to the left. Very good. So to do that, I can take this pair of electrons, move it here, kick out this pair of electrons, and move it back to the oxygen to make it single bond. That is nitrate. Okay, make sure you put on the exam the back and forth arrows. The back and forth arrows. Because one is not more preferenced than the other. It's not. They're all equal. And where do we see the delocalization? See that single bond negative charge? It's not just on that oxygen, but it could be on this oxygen, or it could be on that oxygen. So once again, another stable molecule. Okay, what is this phenomenon called?
Delocalization.
Resonance. But yes, this negative charge is delocalized, but this is resonance. These are the three resonance structures of nitrate. Yeah, let me write that down, delocalization. All right, shall we do one more before we move on to the next topic here? All right, we'll do one more. And this is phosphate. Do you remember putting these on your flashcards? Okay, way back then. Okay, David does. All right, phosphate. The structure of phosphate is PO4 minus 3. Okay. This is called the phosphate ion. What is phosphorus happy at? 5. Very good. It's right below nitrogen. What is oxygen happy at? Okay, but we have 4 of those, so that's 24. And then what does the minus 3 tell us? Okay, 3 electrons. So our goal is to get 32 valence electrons around PO4 minus 3. All right, what do you think the central atom will be? Phosphorus. Nice job. Okay. And how do you think we'll get minus 3 with oxygens? We have to have 3 single bonds and 1 double bond. Okay. Very nice. And how many lone pairs is a single bond oxygen? And what is the formal charge on that single bond oxygen? -1. And that's -1. I'll make this -2. And then can I make this -3? And what should the last oxygen be? Double bond. And how many, Gerardo, how many lone pairs on a double bond oxygen? And what's the formal charge on that oxygen? 0. Okay, so that is phosphate ion. What's the total charge here? -1, -2, -3. -3. Okay, let's count all our electrons to see we have 32. Okay, ready? Count with me. We have to make sure we have 32. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. This is the right structure. All right, let's look at the octet rule and formal charge for the central atom. The central atom here is phosphorus P. Okay, let's first do the formal charge. Ready? Formal charge. Okay, 1, 2, 3, 4, 5. What is phosphorus happy at? 5. What's 5 minus 5? 0. Okay, let's do octet rule. Ready? Count everything. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, is that okay?
Yeah. It's okay. Expanded.
This is called an expanded octet. Very good. Okay, where else can I put that double bond oxygen? Okay, everywhere. You mean to the left, and then to the top, and then to where? To the right. All right, so I'm going to do that. You can follow along with me. So let's first do it to the left, okay? I'm going to take this pair of electrons to the left. So what you guys said. I'll take this pair of electrons, move it here. This kicks it out there. Okay. And this is what we will get. Okay. What's next? You said to the left, and then where else do you want to put the double bond? Where? To the top? Okay, can I put it at the top? Yes, I can. Okay, to do that, I'll take this pair of electrons here. This kicks out this pair of electrons there. All right, and what's the final resonance structure, you guys? To the right. How will I get it to the right? I will move one of these electrons here, and this will kick out this one there. Okay. Oops, here we go. So how many structures are there of phosphate? 4. Yeah.
Oh, are these two because the double bond at top and the bottom just flood, and then left and right just flood. So technically this one two.
Oh, you're saying this
Yeah.
flip? I mean, I guess, but these are 4 different oxygens.
Okay.
So technically, I see what you're saying, Husong, but this oxygen is different than that oxygen. Okay. All right. So on the exam, you don't want to say, oh, this and this are related just because I do a 180 degrees.
Yeah.
No. Okay. You draw all the structures. Okay. And these are different oxygens. Why? Because here the oxygen is negative charged. This oxygen is negatively charged. This is a double bond. So they're different, but they're the same. Yeah. All right, so where's the delocalization of the double bond? Okay, it's across all 4 oxygens. Okay. And where's the delocalization of the -3 charge? Okay, it's across all 4 oxygens. So the -3 is shared equally across these oxygens. So that is phosphate. Okay, so carbonate, nitrate, and phosphate have resonance structures. Okay, there's one more. I'll let you guys do that at home, and or just for practice, it's sulfate. Okay, sulfate has a resonance structure, so you guys can do that. At home, and the goal here is to draw all the resonance structures of sulfate. Ion. All right, so I'll let you guys work on that independently. At home, I'll post the answers up on a later date. Okay, but this is the idea of resonance. All right, let's do something new now. Let's go back to CH4. Okay, CH4 is called methane. Okay. And what's the central atom in methane? And how many hydrogens? 4. Okay. So this is the Lewis structure of methane, which is CH4, which is what we went over on Tuesday. But is this really what methane looks like? Okay, remember all molecules have a 3D geometry. They're 3D, which means some come out, some go behind. All molecules have a 3D structure and geometry. Okay. So methane really doesn't look like this. This is a flat structure on a piece of paper. So we want to draw this in 3D. So the way we draw it in 3D is we figure out the central atom. So what is the central atom here? Carbon. Okay, how many bonding and how many lone pairs are on the central atom? There's 4 bonds and how many lone pairs?
No.
Okay, 4 bonds and 0 lone pairs. 4 bonds and 0 lone pairs. So we're going to take one of the sheets there. All right. And we're going to choose the sheet to determine its 3-dimensional structure. So make sure you have a copy of Table 10.1 and Table 10.2. So you can bring this to the exam. Okay, bring this to the test. Okay. You're welcome. All right, why am I choosing 10.1? Okay. Because the central atom has what in table 10.1? Okay, the central atom has no lone pairs, okay? So 4 bonds and 0 lone pairs, what is the molecular geometry? Okay, so methane actually looks like, has a 3D shape, molecular geometry that is tetrahedral. Okay, so molecular geometry here for methane is tetrahedral. All right, so how will you draw something that's tetrahedral? Okay, we can use this to help us. First of all, before we even draw something that's tetrahedral, what is a tetrahedron? Anybody know? It almost looks like a pyramid. So let's see if we can construct a tetrahedron here. All right. So I'll need a volunteer to come up. Anybody want to come up here? Okay. So go ahead, Alex. Okay, so you're going to take this and screw it in. That's one. Okay, CH4. This is 3. This is 4. Show it to the class. You're holding it? You can hold it any way you like.
Cool.
Okay. So CH4 is not this. Okay. It actually is a tetrahedron. Okay. So you can even set it up on the table like this. So this is what CH4 looks like. Okay. What's this center atom? Okay, what are these substituents or the outer atoms? These are the hydrogens. Okay, so how will we draw this? Okay, first of all, you see my chest? Okay, pretend my chest is a plane. Okay, flat piece of paper, flat plane. Okay, what's on the plane? Hydrogen. What's on the plane? Hydrogen on my chest. Okay, what's coming and sticking out towards you guys? Hydrogen. And then what's coming behind you? This is on the plane. This is on a plane. This is sticking towards you. What about another fourth hydrogen?
Behind.
Okay, it's behind. Okay, it's behind. Okay, so we have to try to find a way to draw this because this is not what methane is. Methane is a tetrahedral, or the three-dimensional shape is called tetrahedron. Right? So let's go ahead and draw this. So when we draw this, go ahead, Alex. Thank you, Alex. Okay, we'll be back for some more. All right. No lone pairs, so you have a very nice bond angle of 109.5. You know, that's just the angle of a tetrahedral. You know, what's an angle of a linear molecule or a line?
180.
180. So a tetrahedral will be 109.5, a very simple angle, because of no lone pairs. Okay, so my chest is flat. This is going up. This is going at 109.5. This is going at 109.5 towards you. This is going 109.5 back away from you. Okay, this we're going to draw with what is called a dash. Dash. Okay, a dash bond. Okay. And this that's going behind you, behind me, behind the plane of my chest, we're going to call it a wedge. Wedge bond. Okay? No, wait.
Yeah.
The other way around. This is called a wedge, and this is called dash. Okay? The one that's going behind is dash. The one that's coming towards you is
The wedge.
wedge. Okay? I'll show you now. So just to clarify it, we'll draw it. This is going to be a, and this,
Dash.
dash. Okay, so there's our carbon. Here's an H. Here's an H. Okay, this is about 109.5 degrees. All right, the one that's going to come towards you. Okay. This is called a wedge. And the one that's going behind, this is a dash. So this is the 3D structure of methane. Okay, so the molecular geometry is tetrahedral. The electron geometry, there's no lone pairs. Okay, there are no lone pairs. 4 bonds, 0 lone pairs. So the electron geometry will be the same. Okay, when you have lone pairs, this becomes a problem. Right now, this is not a problem. No lone pairs, don't worry about it. It's the same thing. So this is how you want to draw any tetrahedron. Now, if I was good in my structure, but if I was a good artist, your professor or your teacher's not Picasso, but technically, if I were to draw a circle across each atom, and if I were to take the center, of each atom, okay, and draw a line connecting the centers. I don't know if you see this, but you will get a do you guys see this? Yes or no?
Yeah.
A tetrahedron. Okay, tetrahedron. And what's the bond angle on this guy?
109.5.
Oh, I forgot this here. Yes, the bond angle would be 109.5. Okay. So, how do we draw a bond that's coming out from the plane of the paper that's coming towards you? A wedge bond. Okay, what type of bond do we draw if it's behind you, going down, away from the plane of the paper, going away from you? Dash. Okay, what about this bond here? And this bond here? That's just on the plane of the paper, right? Okay, so this is a 3D, trying to draw something that's 3D. All right, so that is methane. Okay, the second thing I want to teach you guys is polarity. Is this polar or non-polar? And this will be important when we go to Chem 2, because that's the first thing we talk about. Okay, is this polar or non-polar? Okay, the answer is non-polar. Okay, why is this non-polar? Do you see any electronegative elements here? No. Hydrogen is very weak. It has 0 electron pulling power. If I were to replace one of the hydrogens with bromine, okay, so instead of CH4, which is this, methane, I get CH3Br. Now I'll ask you the question, is this polar or non-polar? What would you say? Okay, now you would say this is polar. Okay, why would you say it's polar? Okay, because of the electronegative pulling power of the bromine. Okay, yes. This is partial negative, this is partial positive. So replacing one of the hydrogens with an electronegative atom will make it polar. But right now, this molecule in question, methane, is nonpolar. Because bromine is electronegative. What are the electronegative elements? The halogens and oxygen, nitrogen, sulfur, some of those. Okay. All right, the next and final thing I want to tell you guys is hybridization. Ugh. That's not good. Okay. Okay, so methane is tetrahedral, molecular geometry, the electron geometry, we don't care because there's no lone pairs on the central atom. It's nonpolar because hydrogen does not really pull. Okay, hybridization. Okay, hybridization means mixing of the atomic orbitals. Okay, so what are the orbitals that we learned in Chapter 7, Chapter 8? There's an s orbital, there's a p orbital, there's a d orbital, and there's an f, but I will not talk about f. All right, so how will we get to 4 bonds and 0 lone pairs for the hybridization? Okay, we're going to take 1 from s, that's 1. And then how many will we take from p? Okay, this is 1, and carbon will recruit 1s. Okay, so we need 4 total. So 1s, and then how many p's? 3. So this is an sp3 hybridized carbon. This is an sp3 hybridized carbon. All right, so that's what we'll be studying from here till the last day of class. We'll be just doing the molecular geometry, the electron geometry. There's no lone pair, so don't worry about it. Polarity, whether it's polar or nonpolar, and then the hybridization. Okay, this is sp3. You see the s is 1. We don't write the 1. Don't write 1 because it's just implied 1. 1 plus 3 is how much? 4. So those are the 4 bonds that it will recruit. Carbon, the central atom, will recruit to get to make methane. All right, so now let's continue to do this. Let us look at, we did another one last time. Okay, let's do ammonia and H3. This is called ammonia. All right, so what's our central atom here? Nitrogen is happy at 5, hydrogen is happy at 1, but we have 3 of those. So we need to get a total of 8 valence electrons. So what's the Lewis structure of ammonia? We have nitrogen, and then hydrogen. How many bonds? 3. Okay, and then what else do we have? 1, 2, 3, 4, 5, 6. Where will 7 and 8 go? A lone pair. Okay, very good. A formal charge on the nitrogen, 1, 2, 3, 4, 5. What is nitrogen happy at? 5. What's 5 minus 5? 0. Hydrogen, 1. What is hydrogen happy at? 1. What's 1 minus 1? 0. Formal charge, 0. Octet rule, 1, 2. Is that good for hydrogen? Octet rule for this nitrogen, 1, 2, 3, 4, 5, 6, 7, 8. Yes. All right. How many bonds and how many lone pairs?
3 bonds. 1
So now we cannot use this one. Why?
Because that's what they're on.
Because we have a lone pair. So we'll use our next table here. So what is 3 bonds and 1 lone pair? Okay. 3 bonds and 1 lone pair. Okay. So what is the electron geometry? Okay, but that's not the structure. What's the overall structure? Okay, trigonal pyramidal. Trigonal pyramidal. Okay. So 3 bonds, 1 lone pair is trigonal pyramidal. Okay. So the molecular geometry is, or the 3D geometry is trigonal pyramidal. Okay, what's the electron pair geometry? Is tetrahedral, but is this molecule tetrahedral? Like that? Okay. Why is it trigonal pyramidal? What causes it to become trigonal pyramidal instead of a nice tetrahedral? Okay, the lone pairs. Okay, so one of the main things I want you guys to know, okay, this is important if you could take organic chemistry or if you go to whatever, any type of chemistry, okay, drug design or want to make a drug. These lone pairs are going to distort the structure. So we have 1 lone pair and they distort the structure. What do I mean by distort? They bend. Okay, they constrict, they bend. Okay? So when you bend and constrict, what happens to the bond angle? It's going to decrease. So it's not going to be 109.5. What will it be then? Something less, because what do lone pairs do? Okay, they're going to do this. They're going to bend, 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 bend. They distort, distort, distort. They bend, bend, bend. Okay. So let's see if we can draw a trigonal pyramidal. Use this as a guide. Okay. So it's tetrahedral, but the lone pair has taken one of the substituents, has taken one of the outer atoms. Okay, I'm going to put it like this. Okay, how will I make a trigonal pyramidal? What do I have to do here? Take out 1. Very good. You go ahead and do it. Can you catch this?
No, I cannot catch.
Okay, fine. He cannot catch it, which is a good thing. I don't want to throw this. All you got to do, he made a good point. All you got to do, excellent, is you just remove 1. Excellent. Okay, what's this here? What's this hole? The lone pair. Okay. So now this has become, you literally like take a hammer. That's what the lone pair did. Okay. So it's no longer tetrahedral. The lone pair has bent the molecule. So let's see if we can draw this 3D. There's many ways you can draw it. There's many ways you can draw this. So on the exam, I'm not looking for perfection, but I just want you to see if you can use the dash and wedge nicely. Okay. So here's my chest one more time. I think I'll have this one go here. I'll have this one go here. And what should I do for this one? Wedge. Okay, and what about here? Yes. Okay, very good. So I'll have this come out towards you guys. That's called wedge. And what about this? Maybe I'll have it go like that. Okay. could also draw, there's many ways to draw this. I can also draw it like this. I can have this go towards you, this goes towards you like that, and then this coming back. Okay, so there's many ways you can draw this. Huh?
We don't use that shear.
The way I've drawn it, you don't have to. I mean, if you rotate the molecule and move it a certain way, you can't get a dash, but right now, this is one depiction. All right, polarity, is this polar or non-polar? That is correct, okay. Okay, why is it polar? What's causing the pull? Not the hydrogens, but the lone pair. Partial negative, this will be partial positive. Okay, finally the hybridization. Okay, so what's 3 plus 1? 4. How will I get to 4? I'll take 1 from S. And how many from P? This, just like the one before, is an sp3 hybridized nitrogen. sp3 hybridized nitrogen. Okay, what's the bond angle here?
Less than 109.5.
Yeah, I do not know the exact number off the top of my head, but the bond angle is going to be, I don't know. I can look at the textbook, maybe the internet, though I'm not a big fan of looking up these things on the internet. The textbook, maybe 108, 107, I don't know. It's not something for us to memorize, but degrees.
Around 107.
Say it again?
Around 107.
Around 107, okay. So that's the bond angle. Okay, it's less than the very nice geometric 109.5. All right, let's do 2 more, and then I'll let you guys go. What are we at here? 10:31? All right, we'll do 2 more. Let's do water, okay? All right, how many total electrons we have to get in water? Oxygen is happy at 6, hydrogen is happy at 1, but we have 2 of those. So our goal is to get 8 valence electrons around the water molecule. So how will we do that? What's our central atom? Oxygen. And then what's bound to the oxygen, Gerardo? 2 hydrogens. Okay, 1, 2, 3, 4. Where does 5, 6, 7, and 8 go? Okay, lone pairs. Okay. So this has not 1, but how many lone pairs? 2 lone pairs, so even more distortion. Okay. How many bonds and how many lone pairs? 2 bonds, 2 lone pairs. What's 2 bonds and 2 lone pairs? So use this on the exam. What'd you guys say?
Bent.
Bent. What's the electron pair geometry?
That would be
Tetrahedral, but it's not tetrahedral. Why is it not tetrahedral? Because what causes it to be bent? The 2 lone pairs. You see, just like this lone pair changes a nice tetrahedral in CH4 methane to trigonal pyramidal, the 2 bonds, 2 lone pairs, those 2 lone pairs actually change something that was nicely tetrahedral. If you remove those atoms, put it with a lone pair, you get something that's bent. So the molecular geometry is bent. Okay, what's the electron pair geometry? Electron geometry is tetrahedral. Very good. All right, how will we draw something that's bent? All right, Alex, how will we do this? It was once tetrahedral. We had 1 lone pair, we got this. What do we need to do now? We're going to remove 1 more. Very good.
You just leave the triangle for the lone
Anyone
pair.
you can take out, yeah. So this is what 2 lone pairs do. Okay? This is bent. So the 2 lone pairs, so this is not the right depiction of water. What do the 2 lone pairs do? Literally, they're doing this to the molecule. Okay? Okay, what's this? Lone pair. What's this? Lone pair. So how will we draw this? I don't know. There's a million different ways you can draw this. I'll draw it bent, like literally bent. Okay. All right, polarity. Is this polar or non-polar? Okay, what do we know about this oxygen? Okay, will this oxygen pull? So this bond between this oxygen and this hydrogen is not a 50-50 sharing, Maria. It's not equal. So who wins in this bond? Who wins? Okay, the oxygen wins. Okay, because oxygen is, what's the term? Electronegative. Okay, so the oxygen pulls, making this partial negative. What will this hydrogen be? Partial positive. What about at the other end? Partial positive here, partial negative at that. So at the center, oxygen. So this is polar. Okay, so this is the reason behind hydrogen bonding, the polarity of the water molecule. Okay. So bent. This is the structure of water. Okay, bent. 2 bonds, 2 lone pairs. Okay, and finally, what's the hybridization? Okay, 2 plus 2 is 4. This is an sp3 hybridized oxygen. An sp3 hybridized oxygen. One of the p's will house this lone pair. One of the p's will house the other lone pair. But this is an sp3 hybridized oxygen. Okay. So let's just do a comparison here. Okay, we had 4 bonds, 0 lone pairs, sp3 hybridized carbon. 3 bonds, 1 lone pair, sp3 hybridized nitrogen. And then 2 bonds, 2 lone pairs, sp3 hybridized oxygen. Okay. So the lone pairs really distort the structure. They're still sp3. They still mix the same amount to get 4, but the lone pairs really, really distort the structure. Okay, and they're going to make the bond angles much less. What's the bond angle here? Okay, probably less than, I don't know what the bond angle is off the top of my head, but it's going to be less than 109.5. Why is it so less? Why is it so distorted? Once again, the lone pairs. All right, what are we on time?
10:39.
10:39? Okay, I think I'll let you guys go. We'll continue this on Tuesday. Have a good rest of the weekend, and turn in your Chapter 8 homework, and start your Chapter 9 homework. We'll be doing this till Test 4. This is what will be happening every lecture.